Hello and welcome to Chapter 4, Earth, Moon, and Sky. After this chapter, you will understand how we plot coordinates on Earth's surface and in the celestial sphere, what causes the seasons and how they differ with latitude, our definition of solar and sidereal days, why we have time zones, our modern calendar, lunar phases, the path of our moon, how the moon affects our tides, and lunar and solar eclipses. Overall, this chapter discusses how astronomy impacts our daily lives here on Earth. Our everyday lives intersect with astronomy quite a lot. We can use astronomy to explain the seasons, phases of the moon, the tides, and eclipses. Questions about our everyday lives can arise from what we have discussed about astronomy thus far. If Earth's orbit is nearly a perfect circle, why is it hotter in the summer and cooler in the winter? Why are seasons different depending on where you are on Earth? We could answer the question of opposite seasons first. This photo is from the Hubble telescope of Australia in December. While it is winter in the United States at the time, in this photo, Australia is experiencing summer. This is because the seasons in the southern hemisphere are opposite the seasons in the northern hemisphere. So our first section is the Earth and the sky. Before we can address our question about seasons, we must discuss how we label locations on our home planet so we can better understand the seasons. We label the top and bottom of Earth's axis as the north and south poles, and the equator as halfway between them. East is the direction Earth rotates. West is the direction opposite of Earth's rotation. A great circle is a circle whose center is also the center of a sphere. For the example, the equator is a great circle. We label the other great circles as meridians. Longitude is defined by the number of degrees between your meridian and a designated prime meridian. So here we can see the location of Washington, D.C. The latitude is the number of degrees north or south. In DC's case, it is 38 degrees north, while longitude is the number of degrees east or west of what we define as the prime meridian. In DC's case, this is 77 degrees west. Each coordinate gives a unique location on Earth's surface. Over time, the agreed-upon location of the prime meridian has changed. However, today, we internationally agree that Greenwich, England is the prime meridian. When we measure longitude, we are measuring east or west of this prime meridian. We define latitude as the amount of degrees you are from the equator. This is the amount of degrees north or south from the equator. So the equator is defined as 0 degrees, and we define the north as 90 degrees north and the South Pole as 90 degrees south. We also have to mark coordinates in our celestial sphere. To do this, we can designate similar measures to the celestial sphere. Declination is measured the same way as latitude is measured. That is, declination is a measure of north and south. What we call right ascension is equivalent to longitude, so right ascension is measured east and west. Before we can answer our question about seasons, it is also important to understand the motion of Earth to understand our everyday experiences on our planet. We accepted that the Earth was rotating since the 17th century. However, this was first demonstrated in the 19th century. To demonstrate this, we used a pendulum. We hang the pendulum over a plane. As the Earth turns, the plane gradually shifts so that the pendulum knocks over wooden platforms around the edge of the plane. This was the demonstration which showed that the Earth was moving relative to the pendulum. The only way those platforms would have been knocked over is if the Earth was moving relative to the pendulum, so the Earth must have been rotating. Our next section addresses our question about the seasons. Contrary to what we may first assume, our seasons are not caused by the distance to the sun. They are actually caused by the tilt of Earth's axis. As Earth travels around the sun, in June, the northern hemisphere leans into the sun and is more directly illuminated. In December, the situation is reversed. The southern hemisphere leans into the sun, and the northern hemisphere leans away. In September and March, Earth leans sideways, neither into the sun nor away from it, so the two hemispheres are equally favored with sunshine. But why does this tilt matter? The first effect we witness of this tilt is the effectiveness of the sun's rays in heating Earth. When these rays are on an angle, they are less effective in heating. When the rays shine directly onto Earth, they are more effective in heating, giving us hotter weather. We can imagine this by shining a flashlight straight at a wall, and then again at the wall on an angle. Doesn't the beam appear brighter shining directly onto the wall rather than at an angle? This is the same phenomenon as the sun rays heating Earth. So in the summer, the sun appears high in the sky, and its rays hit Earth more directly, which spread out less. In the winter, however, the sun is low in the sky, or at an angle, and its rays spread out over a much wider area, which becomes less effective in heating Earth. The second effect we witness due to the tilt is the length of daytime. The days are longer in the summer, allowing more time for this heating to occur. To explain this, we can actually model Earth's path around the sun as the sun moving around Earth. Because of Earth's tilt, we can say the sun spends less time in the northern hemisphere in the months of the United States summertime or June. As the year wears on from then, it spends less and less time with the northern hemisphere and more time with the southern hemisphere. So in the summertime, we have longer days, and in the wintertime, we have shorter days due to the amount of time the sun is spending with each hemisphere. So the final effect from the tilt is that in the summertime, the sunlight has more time to heat Earth, and it is also more effective in heating Earth. Therefore, we get hotter days. In the winter, the sunlight has less time to heat Earth, and is also less effective at heating Earth, so the opposite occurs and we have colder days. On June 21st, we see that the northern hemisphere begins its summer season. The North Pole is constantly in sunlight, and the South Pole is constantly in darkness. On December 21st, the Southern Hemisphere begins its summer, so the North Pole is constantly in darkness, and the South Pole is constantly in light. This is due to Earth's tilt. Because of Earth's atmosphere, we can actually see the sun a bit over the horizon. The sun refracts because of the particles in the Earth's atmosphere to create this phenomenon. This refraction makes the sun appear to rise earlier and set later than if there was no atmosphere on Earth. This is another astronomical everyday occurrence that we see. Our next section is concerned about keeping time. One of the most common measures of time is a day. So most people define a day as a solar day. This is the rotation period of Earth with respect to the sun. However, astronomers use a sidereal day. This is the rotation period of Earth with respect to the stars. A sidereal day is slightly shorter than a solar day. Because Earth rotates and revolves around the sun in the span of a day, so the sun takes longer to reach the same position it started in 24 hours prior, because the Earth is rotating and moving. Therefore, a solar day is about 4 minutes longer than a sidereal day. Ancients used apparent solar time, or the position of the sun in the sky, to tell time with sundials. We can use apparent solar time to define the hours of our day in halves. During the first half of the day, the sun hasn't passed the meridian yet, so it is ante-meridian, or AM. When the sun has passed the meridian, it is called post-meridian, or PM. This is where we get the AM and PM hours of our day. Solar time sounds more convenient than it actually is. The length of the day actually changes throughout the year. For this reason, we do not use apparent solar time. So what do we designate as a day in our everyday lives? Instead, we use mean solar time. This is the average length of a day through the year, which is exactly 24 hours. However, the exact time of noon is different as you move east to west. This is our time zones. Everyone in one time zone uses the standard time of that zone. However, there is a problem if we go around the world and change our watches accordingly. We will add 1 hour each time zone, and when we arrive back where we started, we'll have gained a day compared to those who didn't. Therefore, we have to set up an international date line. It runs approximately along the 180-degree meridian longitude. This is an arbitrarily drawn line where the date changes. When you pass over the line, the date changes to compensate for the added time you received when you traveled around the Earth. Our next section discusses keeping of time in the long term. This is the purpose of a calendar. To be useful, calendars must keep time over long spans and anticipate seasons and holidays. Additionally, the calendar must use natural time intervals that we all experience as humans, like the motions of Earth, Moon, and sometimes planets, in order to be useful. The natural units of our calendar is a day, because of the rotation of Earth, a year, because of the revolution of Earth, and months, because of the Moon's phases. We have difficulties because these 3 periods are not able to divide easily into each other. The rotation of Earth is 1 day. We use the solar day for this since it is the basis for our human experience. However, a month is 29.5306 days. A year, defined by the revolution of the Earth around the Sun, is 365.2422 days. We like to define our time in round numbers. Therefore, these numbers are not convenient for calendars, and that is where the challenge of making a calendar comes in. For example, our year is 365 days, not 365.2422 days. The challenge of a calendar is accounting for this approximation. Stonehenge is an example of an early solar calendar. Some of its stones align with important sunrises, like the solstices. It is thought to keep track of the movements of the sun and moon. Another ancient calendar is from the Maya in Central America. They had calendars sophisticated enough to predict astronomical events like Venus's position in the sky. Here we can see one of their observatories. Instead of accounting for the approximation we previously discussed, the Maya did not use years or months to create their calendar, but instead they were concerned with the passage of days and counting time into the future. Their calendars were just as sophisticated, if not more than, the calendars in Europe at the time. So how did we get our calendar? Other ancient cultures used lunar calendars. The Julian calendar used the phases of the moon to define a month and defined a year by approximately a solar year. They implemented what we call leap years to account for the extra quarter of the day missing from each year. However, we just said that a year is 365.2422 days, not 365.25 days. So this Julian calendar is off by 11 minutes. While that might not sound like a lot, this was significant over time. By 1582, spring was occurring March 11th instead of the 21st. The calendar was now off by an entire 10 days. So to fix this, the church cut the calendar by 10 days. So in 1582, people went from October 4th to October 15th. To fix this in the long term, the church declared that all years divisible by 400 would be considered leap years, rather than every century year. This corrected the extra 11 minutes unaccounted for in the Julian calendar. We call this a Gregorian calendar, and this is the calendar that we use in the United States today. Our next section is on the phases of the moon. The amount of the moon that is illuminated depends on the angle between the moon and the sun. As the angle changes, we see different amounts of light on the moon. So here we can see the moon's revolution around Earth. You can picture yourself standing on Earth and looking at the moon during each of these moments. Take the new moon, for example. The sun shines directly on the side of the moon we do not see. Therefore, when it is a new moon, we do not see any illumination on the moon. As you can see, the amount of light we see on the moon depends on the angle the sunlight is making with the moon. We use the term waxing to describe when the visible light is increasing on the moon and waning when it is decreasing. So when we go from a new moon, we go to a waxing crescent because we are increasing the light. We continue to wax into a first quarter, and then a waxing gibbous, and then to a full moon, and then we begin waning. The moon revolves around the Earth in about 27 days. The moon also rotates about its axis in the same time. Because of this, we only ever see one side of the moon. We call this synchronous rotation. That's because it takes the same amount of time to revolve around Earth that it does for the moon to rotate about its axis. In the first image, we can see the moon revolving around Earth without rotating. The second photo shows what actually occurs. For each quarter around Earth, the moon rotates a quarter on its axis. Therefore, the same face of the moon is always facing Earth. Our next section is about how the moon affects Earth. It affects the ocean tides. Just like the Earth exerts a gravitational force on the moon exerts a gravitational force on Earth. Since Earth is not a rigid point, this force is differential and different depending on where on Earth you are. These forces, over hundreds of hours, produce motions of water and cause tidal bulges in the ocean. It is important to note that the water is not lifted away from Earth. The water flows more towards the bulges, which exist in regions directly under and opposite the moon. So the rotation of Earth carries an observer alternately into regions of deeper and shallower water. This is what we observe at high and low tides. So as you can see, at the high tide we are in deeper water, and at the low tide we are in lower water. During one day, an observer is carried through 2 tidal bulges and therefore experiences 2 high and 2 low tides. The sun also produces an effect on the tides, although it is much less than the effect from the moon. The spring tide occurs when the sun and moon are lined up or at new and full moons. The forces from both reinforce each other. During neap tides, the sun and the moon are 90 degrees, and the force from the sun partially cancels out the force from the moon. Our next section is on the eclipses of the sun and moon. In our sky, the sun and the moon have approximately the same size. The sun is 400 times larger than the moon, however, it is 400 times farther from us than the moon. Because of this, we can have solar eclipses, because the appearance of the moon in our sky is the same as the appearance of the sun in our sky. A solar eclipse occurs when the sun causes the moon to have a shadow on Earth. We can witness both partial and total eclipses. However, we can only see an eclipse at certain points on Earth. Solar eclipses occur when the moon blocks light from the sun. During a solar eclipse, some points would see a partial eclipse, whereas one point would see the moon directly over the sun. However, the moon does not completely block the sun. The sun's corona is visible around the moon. Here we can see the sun's corona, or the thin outer atmosphere of the sun, that is visible during a total solar eclipse. The distance between the Earth and the moon changes slightly throughout the year. Therefore, there are times when the moon is slightly farther or slightly closer to Earth. It appears slightly larger than the sun in our sky and can completely block out the sun and its corona. This is a total solar eclipse. A lunar eclipse occurs when the Earth's shadow is visible on the moon and is visible to anyone who can see the moon. A total lunar eclipse is said to happen if the moon passes through Earth's umbra. Even when there is a total lunar eclipse, the moon is still a coppery color from the sunlight curving around Earth. So how can you view a solar eclipse? Since a solar eclipse is not visible everywhere on Earth, sometimes you have to travel to see one. Here we can see the path of a 2017 solar eclipse. As you can see, the solar eclipse is only visible along this path. So to see a solar eclipse, you have to travel to anywhere on this path in order to see it. Thank you for joining us for Chapter 4. Make sure to tune into Chapter 5 in the next PowerPoint.